Hello, hello, hello. Yeah. No.
Yeah, you can actually talk.
The lights are on, it's right. Yeah. That's what you want to do. Yeah, exactly. That would be great. That would be great. You can certainly put the fingers for them. But I think. But you're too far. Yeah, really too far.
I'm already 1 day ahead.
Huh?
I'm already 1 day ahead.
Oh, I didn't realize that.
If you formulate your teaching, it's hard to make it. But I'll need to run in now, but I'm glad I'm coming.
Yeah, thanks for that.
Very good. So my question is,
Welcome to the ICTS String seminar. So today we have Shailesh Chandrasekharan from Duke University. He'll be talking to us about learning more about the magic of Wilson's renormalization group.
Thank you. Thank you for giving me this opportunity to tell a bit about some of the work that I've been doing, and especially Ashok for inviting me to give the seminar on the almost the final day of my trip this time. Maybe I should tell you a bit about the title. Some time ago, my son is now 12 years old. He was about 5 when we had this conversation about magic. What is magic? And he said, I sort of explained to him that something that you find very surprising, you don't understand why it's happening, but then of course some deeper reason why things happen, and what you find magical maybe is not magical to others because they know the underlying rules. And that's the sort of the key word here. So I'm going to tell you about my perspective, why I find this very exciting and interesting, something I don't quite understand, but I'm sure there are experts who might understand this better than me, and so I would love to get their insight. But more going to the physics, so some of us have been trying to understand if there are ways of building continuum quantum field theories out of just a few quantum degrees of freedom, especially motivated by, of course, this hype about maybe at some day we can do quantum computing, and maybe we'll then be prepared to use those resources. On the other hand, when you try to go back and see how you learn about how you should think about continuum quantum field theories, this seems very unintuitive. So at the end, some things seem to be working out, and I think that's all this magic of RG, and I want to explain to you what that is all about. But I think I should first mention Sandeep, who is a student at Saha. He's done most of the work that I'm going to talk about, at least the new work. We are collaborating. Debashish, again, is his advisor. Marina is at ETH, and I think all three hopefully are online somewhere in the cloud watching this. These are my other collaborators on some previous work that I will mention about. So we have now 2 examples, which is very intriguing, that somehow certain things seem to be emerging out of this magic, and that's the message I'd like to give you at this end of the talk. So the outline of the talk is the following. I'll briefly review, I would say, how, in fact, many of us learned how to think about quantum field theory, especially in the continuum limit, right? How do you define a theory on a lattice, and then how do you take the continuum limit, understand how certain massive theories that we are interested in emerge, right? So I'll explain to you some of that. And then I will talk about this new idea about formulating these theories with just a few qubits, right? And what this idea is, and how all of this matches is exactly the magic, right? And so what I will argue is that somehow even the small number of qubits can perhaps give us the theory that we are looking at. And I'll give you 2 examples, right? This is an older result, and then I will present quite a bit of results that we have recently obtained and the conclusions. The models themselves are very simple. They're not very complicated to understand, but the analysis and all that leads to something very interesting. That would be mine. So let me begin. So when you think about asymptotically free quantum field theories, they are pretty non-trivial to calculate because there's a marginal coupling which is relevant, and in the infrared it becomes very, very large. And so you just have to use some non-perturbative technique. And Wilson long ago explained to us how you might be able to get that, right? So the idea is to start with your favorite continuum quantum field theory that you would write down. I'm going to work in Euclidean space, so imaginary time. That would be my goal throughout. How all this extends to real time is again an interesting question all by itself. So if you start with a sort of a continuum action and you write down sort of formally what type of things that you'd like to calculate, typically they're correlation functions which have all the information that you need essentially. On a lattice, typically we take the action in the continuum and we think about discretizing. So take out all the short distance physics. Essentially, it acts like a regulator of the ultraviolet, and then you write down basically the same theory on a lattice, just the fact that now you have these fields that live on a space-time lattice rather than in the continuum. And that gives us a way of defining these correlation functions mathematically precisely. There are no more infinities to worry about, and everything is very well defined. At the end of the day, of course, this theory is not this theory, so you have to do some interesting limiting procedure, and then at the end, which we call a continuum limit, you go back and understand what the implications of these theories are. So this is just a way of defining the theory non-perturbatively. And this is the way we typically even teach graduate students these days how to do continuum quantum field theories. But we are trying to change the paradigm, right? Because we want to do these things on a quantum computer, and so this is going to be the interesting question. So what Wilson's perspective was that in a space of all lattice models, you just wrote down one of these lattice models. There is one special point. If you figure out where that special point is, you're like God, right? You won't know that in principle. It will be some point in this whole space of lattice theories, and there are some places if you start and if you do your RG, you will reach that point. If you start from some other places, you'll flow away from that point, and so these are the irrelevant and relevant directions, and some of them could be almost irrelevant, almost relevant. These are the marginal directions, and sometimes you might have exactly marginal couplings, and these will be on your critical surfaces, right? So those will be your theories that you're thinking about, but typically that theory will be some kind of a conformal theory. This is not what is interesting. If you're interested in a massive theory, you're going to perturb slightly about that point, and then the physics of that perturbation gives you all the interesting massive theory. So typically you do it in this way, right? Of course, you don't have control over all that. So what you do, you just write down your favorite theory, as I just mentioned in the previous slide, and you tune the couplings of the theory such that you hit some critical point. And at that critical point, at long distances from RG, you get back the physics of that theory. That's sort of the maybe say rule of thumb, right? What you should do. And this seems to work very nicely in many theories, right? So I'll give you two examples. These are the two examples I will then consider later on. So just to get you started. So think about just the O2 model, the very simplest, one of the simplest charged scalar field, if you wish. I'm going to be in 2D because in 2D things are much more richer, so there's a lot of interesting physics there. So if you like the continuum theory, you might say, well, I'm just interested in what we call the nonlinear sigma model, right? This is a two-component vector. It's a real vector. On each space-time point, you have this nonlinear object. It lives on a circle, right? Essentially, and you write down your field theory in a very simple way. And what you do is you just take this, and I can argue for you if you are not familiar that if I just take on each space-time lattice site, now you define just this two vector, take a dot product of the nearest neighbors of two of these objects, and put a coupling minus beta. This is like a classical O2 model. And that, in some sense, if you think about the smooth field limit, goes back to this model. That's basically it. So you've basically done the classical connection between the continuum theory and the lattice theory. But then, of course, as I told you, you have to go back and take the continuum limit. For that, you need to understand the phase structure of this theory. And usually what happens is when you do that, you see that in this theory, there are actually two phases. One is the critical phase, and then there is a massive phase, and then there is a critical point. And this is the PKT critical point. Yes.
I have a question.
Yes.
So when you are talking about this SL, I mean, in general, I mean, this action would not reduce to the previous continuum action because of the derivatives, right? I mean, how do you incorporate the fact that the derivatives are there in the lattice action?
Yeah, so actually the derivative is indeed there if you take this nearest neighbor phi dot phi, because if you take this phi to be some kind of a continuum field, you can actually argue that if you then expand this out in a spin wave approximation, then you will get back this. This is like a standard trick. There is actually a constant piece here. If you write down the second derivative term, there's a constant piece, but that constant piece is, I've just neglected it because it just drops out of my calculation. But this is very standard in most lattice field theory books. If you need more, I will maybe perhaps after the talk, I'll explain to you. Maybe you can go and explain.
Okay.
Okay, so in this case, the physics is very simple. You just have to solve this model on the lattice, and you'll see there are two phases. And notice that if I'm interested in the massive phase, I need to tune myself to this critical point. And as I come to this critical point, I get some kind of a continuum quantum field theory. That is the thing. So with this action, actually the theory that you get is not quite this, and this is something that was worked out long ago. You actually get a very interesting set of theories that there is actually just not only the spin waves, there are also topological defects, and you have to put all of them together. And this was like the famous work of all the physicists long ago. So typically you get a different kind of a theory, and you can figure out what the theory comes from a lattice. And if you don't want lattices, you want to then change the lattice theory and work like that. So for the moment, since I'm going to be interested in this particular theory, I'll stick to this. And the massive theory that you get actually is asymptotically free, because the interaction term actually is marginally relevant in the massive phase. So you can actually write down a completely well-defined theory at that. Of course, you can also do this in higher ON. So for example, if you wanted to do an O3 model, you'll again write down a very similar model, now just a 3-component vector, right? Everything goes through as before, right? It's exactly identical to that. And you can again show that in the spin wave approximation, you get this physics. But then if you really want to know the real physics of the theory, you go back and study this theory. Again, you understand the phase diagram of this theory. And in this case, you basically get a massive phase all the way to beta of infinity. And so the continuum theory from the lattice is defined in that particular limit. So you take this theory, you study this all the way to beta very large, and then you look at long distance physics, and you get back the real quantum theory of that. So that's sort of the usual conventional way of doing these field theories. Again, this is a asymptotically free theory. It's a massive, there's a mass gap that gets generated non-perturbatively, and these are the interesting questions to understand. Now, one of the interesting things about these asymptotically free theories is that there are no free parameters, right? And that's one of the reasons they are holy grail in at least high energy physics. They don't have a non-perturbative mass gap, so the theory doesn't have any scale in the problem, and the scale is generated dynamically for you. And it contains a lot of rich physics all the way from UV to IR. There is no cutoff. Everything is just sort of well-defined mathematical functions, right? Of course, I just talked about 2 examples. There are lots of examples that we'd like to understand. And the physics in all of these things are encoded in some well-defined mathematical functions that connect dimensionless variables, right, at the end of the day. So for example, one function that I'm going to talk about a lot is what we call the step scaling function. This is something that we calculate often on the lattice, right? And this step scaling function is basically, you take this continuum theory. Remember, there's no real scale in the problem. It just comes out dynamically. So if you put the whole thing in a box of size L, then it's like a probe of a new scale. So there is a dynamical scale in the problem, and you're also probing a new scale, right? And so you can then define a correlation length in that box size, this C of L. And then this ratio then becomes a dimensionless number. Right? So this is a physical scale that I'll define in a minute inside a box, right? And that is not the full correlation length or a mass gap in the infinite volume limit, because if you squeeze the box, something's changed, right? So it's like a response to the box. And then you can also ask what happens at that particular thing if I just change the box by a factor of 2, right? How does this change? So this is a very well-defined function of dimensionless variables, and this is for a given asymptotically free theory, this is a universal function. And we'd like to calculate that, for example. Because this is just one of the examples, there are lots of examples like this. And so here is a box size L, and this is the correlation length in that box size. So the way we calculate it is we take a favorite correlation function which has this correlation length built in, right? And then you look at it at zero momentum and look at it at the first non-zero momentum, because if you put it in a box, the momenta are quantized. And then you take this particular thing and you can argue that this C of L will scale with L with some dynamics of the problem. So if you actually see the behavior of the step scaling function, it takes some very interesting form. So for example, in the 2D O2 model that we talked about, if you go approach the BKT transition from the massive phase, this is the shape that you get, right? And that's the universal curve that comes from that particular QFT. Now notice there are some interesting points here. When you so this point, this limit is the large box limit, because in the large box, remember it's a massive theory, so the correlation length will go to something finite, and so L is becoming huge compared to that fixed correlation length, and so this ratio is going to go to 0, and that's the IR limit. So in that IR limit, since the mass gap has reached its value, wherever it has to go, whether I do it at 2L or L, it's the same, so that ratio is 1. Right? In the other extreme, you have to ask yourself, and this is some calculation you have to do in the theory. What will happen is, since there is no scale in the problem, things are all scale invariant. And so what will happen is C of L by L will be a number, and we have to figure out what that number is. And in this case, this number was figured out, and that turns out to be that number. And that's a universal number in this particular theory, right? And then, of course, it's scale invariant, so this particular thing will just scale with the lattice size, so it's 2 there. So in the UV, typically these lines go towards 2. If it's something like the O2 model, it can go to a constant, which is a universal number. For example, in the O3 case, again, the IR is the same, but then you can actually argue that this particular correlation, this number actually diverges, because C of L just looks like some kind of a mass scale, and that's going to go to 0. And so in perturbation theory, you can actually derive what this curve looks like. And again, it's going towards 2. So again, this is the universal curve for the O3 model. So these are what, at the end of the day, asymptotically free theories are all about, and we have to extract them. And if you know of these, actually in these two cases, these are all exactly solvable models, so these curves are completely known, right? On the other hand, in maybe theories like non-abelian gauge theories in 4D, we still don't know how to calculate these. So the goal would be at the end of the, somewhere later on, would be to see if we can really compute these kind of things. Of course, for QCD itself, some of these have been sort of computed. There are, of course, errors to worry about and all that, but so the lattice formulation can be used to compute these universal curves. As I told you, these are just one curve. There are lots of curves like this. Now, the lattice calculation is actually challenging. Why? Because what you are constructing is a lattice model. Remember that there are lots of scales in the problem. Of course, there's a lattice scale where there's going to be all kinds of lattice artifacts. It's not a continuum field theory. But then if you go far enough, long distances, at some point the UV scale starts setting in. And that's where the universal physics begins to come. And then, of course, there's also the IR scale, right? So somehow you have to have all of these scales in your lattice. So sometimes you need really large lattices to be able to study these calculations. And here you will see non-universal physics, but there is whole region you see universal physics. Now, the traditional approach has a saving grace here, right? And this is why we all sort of bought into the idea, right? So we said, the lattice model is not very different from the UV physics. Remember, we wrote down the lattice action, we just discretized it. And so it was looking just like a simple discretization of the lattice, right? It was nothing magical, let's say, using the word. So this connection seemed almost plausible. And in fact, you can show in perturbation theory that everything that you do with other regularizations, you can get with lattice, and so everything seems to be fine. So lattice is a great way to do this calculation. So in fact, this is a real data now. That was just a sketch. You can actually show all this data and see how nicely it falls on this curve, and that is your term. This is in this traditional model. I'll call it the BXY, right? In fact, it's not easy. By the way, even today, as I will explain later on, where the critical coupling beta C is something that's debated, because we will see in a minute, the data is not really convincing. You might say you'll have to do some fits and all that, but at the end, we all sort of agree, okay, yeah, this is the best we can do, and so that's the answer, right? And so and this is a very very famous work which actually does a very nice job of this calculation. Now, for the O3 model, it is easy. There's no critical beta, so all I have to do is to change it to keep increasing my beta. And there, again, this was done long ago, 1994. Oh, yeah. So this whole curve is universal because that is one of the predictions of the asymptotically free theory. So in the continuum, this curve is one of the curves. Remember what I did? I took a continuum theory, put the continuum theory in a box, and studied how that continuum theory affects the correlation length as I squeeze the system. So this whole curve is actually the physics of the continuum field theory. It's not just this one point is one of those predictions, if you wish. But this whole curve is a prediction in some sense. Exactly. So I'm saying this whole curve is the continuum, one of the things that we should try to calculate, if you wish, right, in the continuum. And similarly, there's the whole curve here. Now, this line here is a perturbative calculation, I think up to 3 loops or something like that. Right? Okay. So the traditional lattice theory works, everything was beautiful, right? But there are, of course, other, I wanted to say one more thing. There are other universal numbers, right? In the O2 case, one of the famous numbers that people talk about is what we call the helicity modulus, where this is basically, if you wish, there's a twist in the boundary condition, and then you can ask a susceptibility with respect to that twist. If you like to think in terms of particle numbers, it's related to a winding number. It's related to, let's say, the U1 charge, so it's a current correlation function. There are lots of ways of thinking about this object. So this is one of those another interesting quantities we can calculate on the lattice. Now, in fact, in the UV, this number is supposed to take this particular value. It's actually I was thinking it was 2 by pi, and in this paper it actually says there's actually a small correction to it. It's something that's neglected. But yeah, I think it's pretty small. We'll neglect it as physicists. So 2 by pi is one of the numbers that we'd like to calculate, right? But notice in this traditional model, I'm almost on 2000 square lattices. I'm far from away from this number, right? So if I really wanted to do calculate this particular number from this curve, I will need some finite size scaling, right? People do that finite size scaling and there apparently drops off like a log. And so this is one of the achievements of that paper. So I just wanted to let you know that lattice calculations can still be challenging. Even the O2 model, remember the critical point is between these two, and I'm still very far away from that jump. Yeah, this is the lattice size. I do the calculation, and if I'm at the critical point at infinite distances, this should go to this number. Of course, if you have a better finite size scaling, then it might go quickly. That depends upon the lattice model. So this is basically, remember there's an O2 current conservation. So one way to understand it is a susceptibility of a current correlation function.
I have a question. So this, what do you exactly mean by the helicity modulus? Because helicity takes discrete values from 0 to minus, plus minus half, plus minus 1, etc. Right? So what do you mean by helicity modulus here?
So, okay, let me give you another definition. So, for example, if you think about putting this whole O2 theory in a box, right? Remember the O2 fields will be periodic in time, periodic in space and time. So you can ask yourself how much has that O2 field rotated by the time it came back from one side of the box to the other side. So it will be some integer times 2 pi, right? And so that integer times 2 pi, you ask yourself, what are all the fields that you have generated? And you take that 2 pi times that integer, square it, and you take the average of that. If you wish if that explains to you what that helicity modulus is. You basically average the winding of your fields.
So it's not helicity in the usual quantum field theory sense, right?
No, I don't think I'm using any fermions or any spins here, if that is what you mean. It's just a winding of the field.
I see. Okay.
So, you had a question.
The y-axis, I just want to point out, actually suggest just a few percent of the value, right?
We consider it very bad.
That's very bad.
Of course, you're right, completely right that it's not very far off, but we were looking at 2y pi and this is off, and you can see a big discussion of why that is the case in this paper. So that's bad. Yeah, there's supposed to be a log L correction, and you can get that. And logarithmic dependence on L is bad, so you need, yes. What I mean by universal is, remember I'm interested in something in the continuum, and if I can extract something in the continuum, I call it universal, because once I measure it on a lattice, it will be different from the continuum, right? And there are various lattice descriptions, and all of them can give you different results. But then if you extrapolate it, they all give you the same because you are doing the continuum result. So in that sense, it's universal. So if you're just interested in continuum quantum field theory, you'll say, that's what I want, that's it. We won't even use the word universal, you're right, it can be confusing. But from our perspective, since different lattice field theories can give you different results, they have lattice artifacts, you want something that's the same, right? That doesn't depend on the details of the lattice discretization or cutoff dependence, if you wish. So then it's universal. There's another thing about universality in the RG sense, in the sense that different theories can give you the same physics at long distances because the physics is universal in that sense. It's something similar. The different lattice field theories are living in different points in space. They all lead to the same physics. Okay. So I just wanted to point out this large finite size errors, which is one of the things in the traditional model we live with. So here we have this magic of Wilson's renormalization group count. So if Wilson was right, we should be able to get the same physics from different lattice models, not just maybe changing the first derivative to a second derivative. That's what people do usually, right? They just change different models by just changing a few small things. But maybe we can do something completely different, something crazy, right? So the way I think about it is that maybe this was a traditional model, not just modified slightly here, but just go somewhere totally different in some crazy different way. Keep certain things correct, we don't know what, and can we still come back and get the same physics? So that would be, if I can do that, and then if I can convince you that I'm starting with something very crazy and get back the same physics, I hope that will be magical, at least in the beginning, and then till you understand it, then you understand. So that's what is happening. So this is where this whole idea of formulating field theory is just a few quantum degrees of freedom per lattice side, right? So I would say it's a new type of regularization of QFTs, where we construct the lattice formulation of the QFT, but in a finite local Hilbert space. If you think about it, we'll see in a minute, these traditional field theories, especially bosonic ones, live in an infinite dimensional Hilbert space. If you think about the quantum analog of the problem. And so we'd like to then go back and see if we can reformulate with just a few qubits and still be able to get back all the interesting physics that we want. So you take the full Hilbert space, project it to some finite Hilbert space. Now you don't even have to project it. Maybe there are other interesting, non-trivial ways to do this. But still, it's just at the end, a finite dimensional Hilbert space. So what happens is in a finite volume, the QFT is replaced by just simple quantum mechanics, right? And that maybe a quantum computer could do. Of course, the continuum limit will emerge again using some interesting limits, right? You'd have to take some kind of a continuum limit, and maybe for large systems, you'll have to take a thermodynamic limit, and these are maybe not reachable in the near-term eras in the quantum computer, but still, we're just theorists, so we'll explore what we can do. So here we want to tune to a quantum critical point in these kind of problems, exactly like in the lattice theory. So what will happen is we start with now the qubit regularized theory, lattice regularized theory. Already we have it on the lattice, so in some sense the ultraviolet infinities are gone, but then we even do more harm to the fields. We replace each of these five with some finite degrees of freedom per lattice side, right? We don't do something, we don't keep the full field, we just keep a small number of degrees of freedom. The question is, can we then go back and reproduce our asymptotically free theories? Of course, this is not surprising. We already know many models in condensed matter physics where this is done, right? So in that sense, what we are asking is not new. But what we are, I think, asking is, can asymptotic freedom come out of this? Right? So usually people believe that infrared fixed points come out of this picture more naturally. Getting asymptotic freedom, I think, is a bit more tricky, but that's what we'd like to understand. So if Wilson's RG works, again, we should have a qubit model, but then these two will be still universal. There will be some non-universal lattice physics, which is completely different from even the traditional lattice physics that we have, right? But then in some way, we get back the universal physics. But one thing that is missing in this whole approach is we have no way to sort of do perturbation theory here to show that we start from here and get back this physics. It's a bit uncontrolled, right? So then at least in some spin wave approximation, we could do this. And maybe some techniques like that exist even here. And that's something that maybe I don't know, and it'll be good for me to learn, right? But at least for the model that we've seen, this seems pretty non-trivial. So unlike traditional approaches, there is no guidance between this and this. So in a sense, it seems like magical, but maybe not. Yeah. Is there a question? Yes.
No, so it depends a lot on that projection, right? I mean, what is the Hilbert space that you're projecting onto? If you are projecting onto a small set of states around the ground state, in the actual physical ground state, then
it might work.
Very well be able to capture it. But if you just project it randomly, So
It means-
you have to specify it more, no?
So
And you
you're completely right. So I'm going to show you some results. Then you can tell me whether we did exactly what you wanted us to do or we did something else. So we are being very blind. We're just looking at a single lattice site and we're just removing many degrees of freedom on a single lattice site. So we're not, because remember, getting a ground state is very non-trivial. So we're not even having any of those deep insights. We're just doing, that's why it's all magical. So we're just doing something very blind on a single lattice site. I'll show you some examples.
Surely if I put several qubits on one lattice side, makes sense that I would get a continuum. So then, can you give a more continuum say?
Yeah, I will show you some examples and then you'll see. Yeah, I think these are all the reasons why I find it magical. Yes. 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 So I will try to motivate the magic and then you can tell me whether it's magical or not. I find it very magical.
It's the
Yeah.
and take large D limit. Then do you expect that it will get back a continuum limit?
Can you say that again?
Suppose instead of taking 2 bits,
Yes.
I take D states, D arbitrary. That's D states, and then take the large D limit.
D is dimension,
Number, yeah, some number.
not the space-time dimension. Just, yeah. So yeah, so as you make, remember there's always a projection. That projection I can make it one, right? So in a sense, there is a systematic way to go back to the original theory. That always exists, right?
Yeah, the surprise is that because you have taken any code.
Yeah,
For
very, very
large, you
small.
expect that you get.
Exactly. Then you will get back to the original theory and you're just not modifying it much. And as Subrat pointed out, you may be okay. So then I would not call it magic.
That is, well, yes, you have D, right? You have some pinpoint numbers, so D is 10 to the 16, and that was like 10 to the something. So you are, so I mean, there's not even a real continuum theory where you really are always going to be, but you're saying you can take D rather than 10 to the 16.
Yeah, so I will show you some results and then we both can argue what exactly we've done, right? So,
Sorry, I have a question.
Yes.
So this, I mean, if you want to get to the continuum limit, and if the continuum limit is just the free scalar field theory, of what use is it? Because I mean, a free scalar field theory is solved. I mean, there's nothing to be done about it.
So I'm not getting the free scalar field theory, I'm getting the whole perturbation from that free scalar field theory, right? So for example, the O3 model in the ultraviolet is free, but in the infrared is a very non-trivial, interesting model, and you can go back and look at all exact results, and it's a really beautiful theory. And we believe that many asymptotically free theories are exactly like that. In the ultraviolet, they look free, but you cannot just say, oh, it's just free theory. There's a lot of physics there.
Yeah, but I mean, the discrete model that you're using, how does it generate the relevant interactions?
Yeah, so it will have the whole universal curve. I will hopefully convince you that we can reproduce. Okay, so let's look at the O2 model first. What are we going to do? So originally, how much time do I have? Can I go on? Or?
Yeah, you can go.
So the original model, remember, was on each side there was there's a two-dimensional vector. So it's like a quantum particle on a circle, right? So that's the degree of freedom per side, per lattice side. So if you go back and look at it in terms of its Hilbert space, you can go to the position or the momentum basis, right? Just angular momentum or the position of the particle. And it's an infinite dimensional space. And so what we want to do is replace it by just a few degrees of freedom. And so we'll take this full space and project it to something. And we don't know what that is at the moment. So let's think about it as a projection. So, of course, at the end, the magic of RG suggests, from what Wilson explains, is that you have to keep certain physics intact, right? So symmetries are a good thing to begin with. So we'll keep, in this case, the O2 symmetry intact. And so we go to the go to the angular momentum basis because each angular momentum sector is a representation of O2. So we just go to that and then project it to some set of m's, right? You just choose some m's. And you can choose whatever m's you want, and that will give you a qubit regularization of the problem. Of course, if I give you a particular qubit regularization, doesn't mean I'm going to get back my asymptotically free theory. That is sort of the goal, but at least to begin to play with what we can do, right? And so the qubit regularized Hilbert space will be much smaller, right? Depending on what m's are. So here I'm going to choose 0, 1, and -1. Those are the only three things I'm going to choose. Now, of course, if I think in terms of, I'm going to assume that they're particles. So in some sense, this is like a Fock vacuum state. This is like a particle of charge 1. This is like a particle of charge -1. And in my model, I see that sometimes I'm allowed to have the charge 1 and -1 top of each other. So in some sense, it's just a 4-dimensional Hilbert space. That's all I'm going to keep, right? And so I'm truncating the Hilbert space brutally, right? I'm just having, basically, the full theory has charged particles. On each side, you can have any charge. That's what is e to the I phi. And I'm saying maybe the physics just requires one Fock vacuum and one charge, positive charge, and one negative charge. That's it. And sometimes they can come on top of each other. That's it.
Why dimension is 4?
Pardon?
4. Why 4? Dimension is 4. Why 4? It is 3. Why?
Well, the 4 is because I'm allowing both 1 and -1 to be on top of each other sometimes.
Well, not on. Basis consists of 3 orths or 3 orths. Well, 0, 1, and -1. How
Yeah.
is 4?
Right. I'm sorry, maybe the slide is a bit misleading here. These were the things that I started with, but then in terms of the Hilbert space, I will allow, in a minute you will see the configurations in my space, and you'll see sometimes I have 1 and -1 on top of each other. So that's why I say it's 4.
Thank you.
Yeah, okay. Okay. So here is I'll give you a sample configuration. Remember, in the classical case, the configuration was a 2 vector at every space-time site. Here is the configuration of my qubit regularized field, right? It can be an empty site, which was the 0. It can be a plus or a minus, depending on how the loop goes, if you wish, right? Each loop has 2 orientations. And sometimes notice there are 2 on top of each other, right? So this thing could have been on like that, right? So that's why I think I would say there are 4 sites per 4 states per site, and that's it. That's my theory. And however you want to count, it's fine. Right? Those are my configurations I start with. Right? These are just the classical configuration.
Just to understand your notation, at each site, depending on whether the arrow is say to the incoming or outgoing, you say it's 1 or 0.
Yeah.
1 or -1.
Yeah.
And then the loop on the top right, you're saying corresponds to 1 -1 because you allow only those kind of configurations, or then you allow multiple loops there and so on. Or
So no multiple loops. Only that. So this is a space-time lattice model, right? I can think about, from the Hilbert space perspective, I can think about a continuum theory, continuum in time, because I have a Hamiltonian, and then I can evolve it in time, and then I would say there is a Fock vacuum, maybe an A dagger plus 0, maybe A dagger minus 0, and then A dagger plus A dagger minus. Those are the 4 states that are possible. And then don't imagine, yes? On the sites. You can, yeah, in a minute. So this is again, in quantum mechanics, it's easy to think about it in a bond. I'll show you in a minute that the degrees of freedom can be thought of as in bonds. Yeah, that's another way of thinking about it. Perfect. That's another way. But then you need also something to do with that. I'll show you in a minute what happens. But for the moment, to answer the question, think about these as just Feynman diagrams of two charged particles. Right? One is a particle and one is an antiparticle, if you wish. Right? So this is just a vacuum sites. This is a particle-antiparticle creation annihilation event. You can think in this language if you want. Right? So this is just decorated in a lattice. That's all it is. Now, as you pointed out, the same model can be thought of as two layers of dimer models, and these where the bonds live, where things live on bonds, right? And then these sites are dimers that connect the two layers. This and this are completely equivalent. If you're not convinced, just spend some time. I'm sure you'll be convinced. Right? So these two are completely equivalent lattice models, right? Here the U1 symmetry is sort of clear. Here the U1 symmetry is somewhat hidden. That's all. So I like to look at it in this language just because now I can think about these as U1 currents going through my lattice, right? In fact, I can remember one of the helicity modulus was related to the winding number. I can calculate it more naturally here, but there is of course a calculation.
Sorry, are you trying to suggest that this entire lattice model has a Hilbert space dimensionality of 4?
So this is if you look in the quantum language, yes, that's what I'm suggesting. Because this is like a classical space-time lattice model, but you can think about it as one lower dimensional quantum Hamiltonian model. And there I would argue that it has four-dimensional Hilbert space.
Okay.
At each site, yes. Yes, at each site.
Oh, at each site.
At each site.
Side versus so we have drawn it, it looks like that you are in the left-hand picture. No, the left-hand side, yeah. That you are associating the states with the bonds, right? Because lattice sites is a little confusing because there are two things coming, two arrows in the side. What state will that be?
Yeah. So since this is a space-time lattice model, it's hard to understand what's going on. You're completely right. I myself get confused sometimes. So the way to think about it is that take one of them to be time and then make that continuous. Don't think about it as just finite lattices. Put a lot of time slices here. Then you'll see that it's like a particle coming in and just hopping to the neighbor and going and hopping to the neighbor and going. Right? Here, there's a Fock vacuum. There's no particle hopping there. So here, for example, what has happened is at some point, pairs got created. So there's an A dagger. One is positive charged and one is negative charged. And this arrow was just a label to just say that it happened in a single site. You can imagine that in a thing to happen like this if you want. And pardon?
Can they touch the corner? Can there be here there is a touching, right?
Yeah, so you mean to say periodic boundary condition?
No, not periodic. Could there be another loop, for example, which starts at that corner, right? Can a corner be shared by four?
So each loop has only one loop, if you wish.
Yeah, that's true. But could there be another loop which touches the same corner?
Here?
Yeah.
No, it cannot come like this. So this side is occupied. So this is like, it's only going to go like this. It's going to be self-avoiding. That's the whole thing about the discrete model. I just have a few states and whatever dynamics it does, it does.
Right arrow, left arrow. Like if you move the left arrow after that, one gap to the right.
So which here?
Let's look at that line.
This line. Okay. Yeah, okay, fair enough.
Right arrow, gap, right arrow. And then there are two left arrows. Now if I move the left arrows one space to the left, I think you would get the thing where things were colliding. You're saying that is not allowed.
Yeah, that is not allowed.
You can have right arrow and one more right arrow, or you can have right arrow and space.
Exactly.
You can't have right arrow.
No. Right.
And then you can do what you like in time.
Right. So just, I think, just to understand, imagine that there were two charged particles, plus and minus, and they are moving on your lattice. They can get pair created and destroyed. Think about this as just Feynman diagrams of two charged particles. That's all it is in position space. Right? Now, just wanted to let you know that if I look at it in this language, these bonds which connect the two layers are just these points, right? These are the Fock vacuum states. In fact, they will play a very important role in my model. That there will be weights. Now, remember, these are just configurations. To give you a model, I need to give you a weight for each of these configurations. And the weight in the classical description was obtained from classical continuum model, and we had, remember, this derivative terms and all that. Here, I can choose whatever I want as long as I can get back my continuum physics. That's the goal, right? So I'm going to be sort of creative here and give weights for all of these bonds as one. We'll see in a minute later on. And these will be the weights which will have another weight, some kind of a fugacity, if you wish, of these bonds or these Fock vacuum states, right? In the limit, as that fugacity goes to 0, there cannot be any Fock vacuum states, right? Because in the theory, this just has 0 weight. That means that these bonds are not existent, and these two layers become two completely independent close-packed dimer models. And this has been studied long, long ago by Castellane, Fisher, and all those people. And we know that's going to be critical. And this is going to be one of those critical points that I'm going to talk about, right?
On the low layer, you can have an opposite or the empty.
So the rules on the dimer thing is take your lattice, define each side to be even or odd. In the lower, if this is an even side, arrows can only come out of that even side. That's the rule on the lower. On the up, if it's an even side, it can only go in, right? And those are the rules that you make. So for example, on an even side here, you'll only have a bond that goes up, and that will be an even side on that, but that will be only coming in. So it's all consistent rules.
Even side here, arrow come out, even side there, arrow.
Exactly.
And odd side arrow.
Exactly. And now if you squeeze both the thing together, you get this. So in the limit, there's a limit where the two layers will decouple. This will play an important role for me later on. Okay. What about the O3 model? Well, I do the same thing. Given the time, I will go a bit faster, because stop me if you need to. Now you have a particle on a sphere, not on a circle, right? And so again, I look at the Hilbert's. Yes.
What's the interpretation of this sort of +1, -1 in terms of the two-layer timer? Yeah, that left right corner thing, the +1, -1.
Oh, this one?
No, the small two-side.
Oh, here.
Yeah. What's the interpretation?
So there in this thing, it's just the same link on both sides. So if I squeeze it, I get that. Okay. So about in the O3 model, you go the same procedure. Here, the Hilbert space is a bit more tricky because your particle now lives on a sphere. The natural representation space of the O3 is the momentum basis or the angular momentum basis. So we do the same thing. We take the full, we project it to some set of L's. For every L, we choose all possible N's, right? And then we do the same thing. And in this case, the simplest will be again 0 and 1. And again, it's 4-dimensional. So here it's sort of maybe more natural to think about it as 4 dimensions, because you can actually think about it in a Hamiltonian picture to having 2 spin halves. and that gives you a 0 or a 1, right? Spin 0 or a spin 1. Okay, so what are the Euclidean configurations? Well, in this case, since it's a spin 0 or spin 1, again, there is some some conservation law, and you can show that that conservation law basically says there are Fock vacuum states. But now loops come in three different entropy factor, right? So each can be going like this or like that. That was the O2, but then there can also be a loop which is not oriented. So there's a non-oriented loop also there. So if you put all of this together, this will be a natural space-time lattice model. But unfortunately, in this case, something that gets hidden is that each spin actually is made out of 2 spin halves, right? Each thing can be thought of as 2 spin halves. Remember, this can be thought of as a singlet of 2 spin halves, and these can be thought of as a triplet of 2 spin halves. So if you actually think carefully about what this Hilbert space looks like, there can be models where you actually, now I'm going to the Hamiltonian picture, right, which is where we learned something new, that, for example, I can take a spin half. Remember, a 2-dimensional theory can be thought of as a 1-dimensional quantum Hamiltonian. In this Hamiltonian, I can think about a spin half layer and a spin half layer on top, right? So this can be mapped to something like this. It's just that then we'll have to keep track of the spin half indices of these spin 1 particles. And in charisma, you do this many times, and they call it deconfined objects, right? So a spin 1 can actually be deconfined into 2 spin halves. So hidden in this, and this is going to be non-trivial, so I'm not going to get into the details of how we can do this, but you can convince yourself that I can start from this and write down a model that looks like this, but then you'll have to keep track of how the connections are, what happens, and the model looks pretty non-trivial. Yes? I'll give you a Hamiltonian in a minute. I'll explain the Hamiltonian in a minute. Right? So again, all I'm trying to argue here is that the space-time model that has configurations like this can come from Hamiltonians that look like that. Right? In fact, we studied this model in the Hamiltonian picture first, and so that in that picture it will become easier what it is. We can notice there is a limit where I can decouple the 2 halves. Right? I just have to put these couplings to 0. The model will look like this, but then there is a limit where the 2 will decouple. So there is a spin half layer that is coupled, and then there is a spin half that is not coupled. Right?
Sorry, I didn't understand why you have the small loops, because I thought now you don't have things on top of each other.
Yeah. So maybe it's unfair because I'm thinking about this as a space-time lattice model, but you're completely right. If I think in the continuum time, the small loop will not exist, it will just come like that. This is just a sort of a space-time version of that model, but you're completely right. So there are subtleties that these things could be unlike in the previous case. But on the previous case, what I would argue is that, so this is a subtlety between Hamiltonian and the space-time lattice language, right? In the Hamiltonian, you have the luxury of a continuous time. In space-time approach, that thing gets squeezed. And so these have weights which are then extended. That's all happens. And so you have to understand how that measure happens and what is the weight. At the end of the day, these are details of the lattice model, and finally, the goal will be whether we can create them a continuum physics or not. And that's the way to think about it. So again, all I wanted to argue is that there are limits where the 2 will decouple, right? So it's like a decoupled point exists. In fact, in this case, if I decouple this, there will be a chain which is critical, like in this other case. Okay, so in this case, we studied the asymptotically free O3 model. This is an older result, so I'll just quickly flash. The Hamiltonian spin-tie is exactly this. So what happens is you have a chain which is coupled by this usual spin chain, and then these do not couple to each other, And so we call it a comb-like model. There is a connection here and they're all sticking out. There is a coupling between these two. And you just write down a simple antiferromagnetic coupling between them. The critical point is when J becomes very, very large. Remember, I need a critical point before I can show you that the physics of the continuum will emerge, right? So the critical point happens when J is very, very large, or equivalently, you might think about a point where these two are getting decoupled essentially, right? They're not quite decoupled because if I decouple them, then I get a different physics, right? I get a spin chain, which is spin half, which is not the two-dimensional massive O3 mod. So I shouldn't go to that limit, but I should approach that limit. That's the physics. And so here are the results. And this is where the magic of RG I will talk about. That this physics is able to reproduce this dark line is the traditional lattice model line that I talked about, right? And this model, notice for small j, falls off because you are on small lattices. Remember, RG means that if I choose a particular thing, as I make the RG big, that is block my theory to larger and larger lattices, I should then see the infrared emerge, right? But then if I want this region, which is the ultraviolet, J equals 3 is not good enough. I need to go to a larger J. If I go to J equals 5, I again start off somewhere and then I follow this. And the reason this is very magical is because on small lattices, this is actually 12, 24, 48, and so on, right? Even at 48 squared lattices, I'm not seeing anything universal here. The only way the universality comes is when you go to bigger and bigger and bigger systems. So it comes off from some other critical behavior, which is where these two are decoupled. And then as it flows to the right critical point and then starts flowing on the RG trajectory.
This numerics is done using Monte Carlo?
Yes, Monte Carlo. Yeah. So again, here, for example, roughly on 500 squared lattices, when it starts turning back, and of course, we don't have the computing power to go all the way there. So here, the correlation lengths are roughly on the order of 200,000 in lattice units, right? And that's part of asymptotic freedom. Now, this is older work. I still haven't come to my new work. Yes. So in this case, we haven't found much difference. So there also they go to these kind of lattices and do the same physics. It's not like much bigger or anything like that. It's roughly on the same order. There may be, instead of 10, it may be 15 or something like that. It's just a few percentage different. We haven't done a good comparison of that. But you didn't have to go to, because remember these calculations were done 15 years ago and not 15, 25 years ago now, right? And you know how the computers were there. It's about the same lattice sizes. Now let me come to the new work, right? And this is even more surprising. So here, remember the lattice model that we said was just this simple O2 physics, right? Just the charged scalar field. And this was this model. When lambda is small, and this is the weight of these instantons, we call it instant. I'll explain to you why that is later on if you need to learn. So we call these as instantons, and then the weight of these objects are lambda. And when lambda goes to 0, there are no such interlayer dimers, right? And so the theory is actually critical. When you put them exactly equal to 0, you get the Castellane Fisher model. But when they go to 0, this was actually studied by people from TFR. Kedar was involved. And they realized that there was a BKT transition there, but they did not saw some very interesting crossover phenomena. And in that paper, they say that this is very interesting, but we don't know how to explain it. And I'll show you that this is exactly the asymptotic freedom, right? So let me argue that the UV physics emerges when lambda tends to 0, but not 0. So here is a plot of this CL by L versus L, right? Remember, this quantity needed to go to this universal number for large in the UV. So notice it starts off at small lattices somewhere in some completely different place. It goes down first, and that's because it's going to this other critical decoupled fixed point value. This was this Fisher Castellane work, right? But then it realizes, no, I cannot go there. I need to change my trajectory, and then finally it goes to this universal curve, universal prediction, right, of BKT. The physics. Remember, I'm in a massive phase, so this cannot be the end point of my calculation because it's going to go up and then has to come down, because in a massive phase, remember we argued that the CL by L will finally go to 0, right? So this is just a temporary crossover phenomena where it's reaching this magical number at some particular values, 2000 lattice sites, right? So before I go to that, I wouldn't even be able to tell you that this model is the same as the UV physics of the BKT transition, right? I just wanted to compare. Remember, this number was also calculated by the traditional model. Notice they are different. And you asked me whether this is bad. Yeah, it is bad. See, I can get a much better result using my simpler model, right? Now, what happens in the full? Pardon? Yeah, same number of lattice points, exactly. Notice. Not only this number, you'll see that, see what happens. I have different lambdas, right? Remember, as I go to lambda 0, that's where I'm approaching my critical point. So at lambda very, very small, it's supposed to come from some strange place that's given by Fisher and Castellane. It decides to change its course. The RG says, hey, finally, you need to go here, and then it'll come back like that. So hopefully this should convince you that the lambda parameter is the tuning parameter that comes closer and closer to the asymptotically free theory. As I make lambda 0, I get closer and closer to this whole theory. Right? So that's the way I recover from the lattice the continuum BKT massive phase. Right? And this is what was very magical. It starts from completely strange and crazy, turns back, and then finally approaches that point. And now if I had bigger and bigger lattices, unfortunately I don't, but I don't know how big I need, it'll whole come back like that. What is that? Oh, here, I think the biggest we have is about 2000 by 2000 in this case. So the green also sort of goes there, but we haven't been able to, by 2000, I think we've lost steam actually. So here the red, notice at 0.4, it goes almost there and then it starts to come back here. And you can actually see that.
I'm confused about this issue of why these simpler models are better than the that somehow seems to go, you see, you just said it bigger and bigger lattice. It suggests if you increase the number of degrees of freedom and go closer to the continuum, you do better. But here you're going away from the continuum and you're is there some physical understanding of this?
It's magical for me. Let me show you some more data and then I'll stop. Let's look at the helicity. Yeah, go ahead.
There is too many degrees of freedom, too many lattice calculations.
Could be. Somehow, if you start with something small and then slowly build up, that's better than having a lot. Possibly.
And maybe if you went to 100,000 lattice, then you make it become worse again.
I doubt it.
Wasn't that the spirit of the question? If you increase the number of degrees of freedom, you might get
But,
It's not always clear.
but there's a difference between UV fluctuations and IR, right? This is not at the UV level. And I think his point was more to do with UV. I don't know.
Fluctuations of the log of this fluctuation.
Yeah, exactly.
Also need the spy fluctuations at every site.
But the lattice fluctuations are actually making the continuum really bad. You don't care about the lattice.
So I think this is, in my opinion, this is teaching us that the lattice degrees of freedom that live on single lattice or single links are hyped up. We can live with some different degrees of freedom, and the real physics could emerge from long distance more natural. In fact, I will also show you this helicity modulus. Notice that the helicity modulus I showed you in the traditional model was there, and there was this question that this was not very far away, but notice here, I can actually show that this comes beautifully to 2 by pi, right? And this is the decoupled value, right? So lambda equals 0 is different from lambda not equal to 0. Now, I don't think we are there yet. That's a good point.
Sorry, fxy and bxy. What is the difference? Fxy and bx.
That's why we call it fermionic, because we got it from this discrete degrees of freedom. We bxy is your traditional xy, the bosonic xy.
Thank you.
Well, if you want to get like dimension of Hilbert says 4,
Right.
if you increase that, like say next L value or something, is the expectation it will get even better, even saturate even better?
I don't know. Maybe there is a magical value of L equals 7 where it will be the best. I don't know.
All those lines, you reduce the number of dimension of the Hilbert space at each side. You still expect this behavior from 4 to say.
I think we've just done very slowly. I don't know how much. 0 is there's nothing left. There is no dynamics. 1 and minus. It might work, but
it came from 0. I mean, in some sense, you're giving some very small weight to 0, right?
yeah, and in this case, the 0 was the perturbation somehow, right? And so somehow 1 and minus 1 was the main thing, but the 0 was the marginal perturbation. Yeah, yeah.
What did you find that this kind of picture that you have? What does that mean? That means that you have like a gas of these loops.
Exactly.
But very few of these instantons.
Yeah, they're very dilute, but then you need to go to lattices bigger so that they can start seeing the effect of that diluteness, right? That's where the physics of, till then it's flowing in the wrong direction. And then it sort of realizes, hey, I'm in a different theory and those things are creating the right physics, right? So, yes.
That's also very non-intuitive from the point of view of the traditional lens.
I completely agree with you. This is why, in fact, one of my slides I told you that I start with some theory which has no intuition that it is real any Gaussian theory to begin with. Yeah, so that is the
Giving this values much faster than
right. So in a sense, I think there's something for us to learn, and I don't know. And so maybe somebody in the audience could help understand. So it seems like, so here all the same thing. So let me go and tell you so the RG seems to be working in a very interesting and a new way, right? So here is my cartoon of what's going on, right? This is the fixed point that I'd like to approach. Apparently, there is another decoupled fixed point, right? Which is what these two models are showing me. If I have a lattice theory that's tuned to that fixed point, right? And I perturb it slightly, I go to a massive phase, but that massive phase becomes massive as it goes closer and closer to this asymptotically free fixed point. And so that suggests that there may be something connecting these two, and I have no idea what this is. So somebody here, if they have an understanding of how there are flows between various kinds of fixed points, could give us a guide of how to start with this, right? So this is what seems to be happening, at least in these two models, that you have some other fixed point, which is not the fixed point you're interested in, but somehow there is a coupling between the decoupled theories, and then it flows to another point. It doesn't flow to that point because you're not ever going to hit that point. You're going to go closer and closer to it, and that's exactly what asymptotic freedom is all about. Now, this reminds me of deconfined criticality. I don't know if there is a connection, but maybe this is some kind of deconfined critical point, and then you change certain things, and then you're going through. People observe all kinds of, I think, slow crossovers and all that. So is it possible that there is some vicinity of another asymptotically free fixed point? That could be one possible thing to think about. I don't know much about it.
Yeah, this is actually a deconfined critical point on this lattice. It's called the Rock-Wilson point.
Oh, there you go. Okay, so there. So is it known that it's BKT?
No, this other orange one.
For the O2 model.
For the O2.
I see. Okay. So we should talk more about that. Yeah. So have they looked at this asymptotic freedom?
Yeah, this is this work by Shivaji Sondhi and Roderick Mosner.
I see. Okay, so there you go. So we have to figure out what they've done, right? Okay. So anyway, let me present my conclusions. I hope that I've convinced you that this Wilson's orogeny is sort of very magical. There are lots of ways to regularize QFTs, right? We showed two examples here. Is this a tip of the iceberg that there are lots of other models that we can actually do it in this way? Are there connections to deconfined criticality? And that will be. Yes.
Thinking as you are talking about how to do it on a simple given lattice case, let's say +1 matrices. So what would you do there? You would simply replace the links by these, these are representations. One.
Yes.
And then in some way I didn't understand quite how do you sort of gauge invariance would be perhaps integers adding up to zeros. How do you write down a Hamiltonian for that?
So that's something that is reasonably straightforward. All you have to do is look at the Hilbert space. That Hilbert space naturally has a left and the right gauge invariance, right? And so, and I can do this for any SUN. And so what you have to do is to write down states which are all gauge invariant to begin with, or you can impose it later on if I want to. So the question was, how do you write down a Hamiltonian? Or?
Usually you have this Kogutsas kind of Hamiltonian.
Right. Right.
So of course you have to impose Gaussian law that the electrically match vertices. So if you have a very simple model like this, I can understand how Gauss's law will come about, but I don't see the interaction. Electric mean square plus magnetic.
So it depends upon, I guess, the representation, right? So in your representation that you have, maybe the E square are all sort of trivial, maybe, because you just get, in your case, are you keeping 0, 1, -1 maybe on each link, let's say?
Compute with the elements on the link, right?
Right. Yeah. So the electric field will be the variable of the representation. It'll just be the 1, -1, and 0. Remember, it's U, which is e to the I5, and its conjugate variable is just the, yeah, exactly. It's just the angular momentum. Yeah, there are calculations which are already doing that. In fact, in 1+1D, people are showing that you can actually get reasonably good results with JMAC in actually SU2 with representations up to 3 halves. You can actually reproduce lots of interesting physics. So there's a group in Munich which is doing tensor network analysis of these kind of things. They're beginning. So it's like a big industry these days, trying to understand. Sure.
So this kind of magic things that you're talking about, are they, like specific lower dimensions? Sense that because sometimes like higher dimensions you expect certain leafy intuition to be, good, and weird things cannot happen.
Could be. I have very little intuition beyond what I'm just seeing. So you may be right. So is there any reason why somehow certain things that work in 2D cannot work in 3D? Now, since I'm reproducing Gaussian theories at the end, I thought that they will extend, but maybe somehow it doesn't work that way. I don't know. Can I?
Is there a version of this in 3D?
We haven't yet done that. Yeah. So this is one of those, maybe in a year or two, I will come back and say it doesn't work or works.
Are there any more questions? No, let's thank Shailesh.
Thank you. So we should talk what exactly is done. Maybe all this is already done.
I think